So as well as determining how we can work with the speed of sound, as well as learning about what's called resonance, we're also going to be talking about beat frequencies. And most of this today deals with sound. There's a little bit that's not sound related, but most of it is now dealing with sound waves. To begin with, we learned yesterday that the speed with which any mechanical wave can go through a substance depends on the substance. And to simplify this explanation a little bit from yesterday, I think it makes sense that if a substance is thicker or thinner, the speed with which the energy can move through the substance changes. With sound waves, it's a little bit more complicated than just talking about the density of the air that the sound is moving through. Essentially, hot air means all of the molecules in the air have more kinetic energy. Their kinetic energy is not organized kinetic energy. It's not like all of the molecules of a baseball having kinetic energy when I throw the baseball to you. That means all of the molecules have kinetic energy and they're organized. They're all moving in the same way. When you heat something up, the kinetic energy that you give to all of the pieces of the substance, in other words, all of the air molecules, is randomly oriented. So on a hot day, some of the air molecules, and by the way, when we say air molecules, there's no air molecule. It's not like a carbon dioxide molecule. There are CO2 molecules, there are H2O molecules, there are oxygen gas molecules, nitrogen gas, probably some toxic molecules floating around in there. So I'm talking about in general the molecules when I say air molecules. They're all moving faster. Now, when you have, and I suppose I can bring this up again, I have it accessible. When you have a longitudinal wave, I mean, this is an oversimplification. You understand that a sound wave does not consist of a bunch of organized molecules that line up in vertical lines. But the bottom line is there are collisions between the molecules in one place as they move towards the molecules further away, and that collision is repeated over and over again. But if the molecules are already moving faster because it's warmer air, the time it takes in between the collisions is less. So for sound in air, if the air is already moving around randomly faster, it's going to take less time for the wave to move through it. And what that means is, as the temperature of air goes up, so does the speed of sound. Okay? And it turns out that at 0 degrees Celsius, and there are other issues here like the density of the air, you know, the speed of sound on a mountaintop where the air is thinner is going to be different than the speed on the surface of the earth. But generally speaking, we use the number 331 meters per second at 0 degrees Celsius. And it turns out that after you pass 0 degrees Celsius, the speed increases in a proportionate manner to the temperature. And it turns out that for every degree Celsius, the speed goes up by 0.6 of a meter per second. So this is a formula that we can use to calculate the speed of sound. It's not a complicated formula. However, it's not on your formula sheet, so you would be given this if you were ever asked to use it. It's not something you need to memorize. Okay? So a very quick example to begin with. What is the speed of sound in air at 25 degrees Celsius? And you're going to be seeing examples that you'll work on later today, which might not just ask you this. It might say that the temperature of the air is 25 degrees, 25 degrees Celsius. How long does it take a sound wave to travel 2 kilometers? So you'd have to use that relationship that is on the previous image here, this relationship. You'd have to use it to find the speed, so you could use speed equals distance over time. But as far as questions go, this wouldn't rise to the importance of an exam question. It's too simple. But we can do the calculation nonetheless. The speed is equal to 331 plus 0.6 times the temperature in degrees Celsius, which is 25. So it's just a matter of working that out. I want to say 346. Is that right, Mark? So about 346 meters per second. So when we do the lab that we're going to do collectively as part of the lesson, and we measure the speed of sound, right now in the room it's 20.3 degrees Celsius. And now I'm going under an assumption that this thing is accurate. I don't know how accurate it is considering some of the equipment that they've installed in this classroom, but if we go with 20.3, part of our analysis in the next day or two, I'm pretty sure it'll be tomorrow, but I'd have to look, would be to take that 331 plus 20.3 times 0.6. And this would be the theoretical speed of sound in this classroom, so when we do this lab, we'll have something to compare it to. We'll be able to do a percent error. Number two, again, this doesn't really have much to do with that temperature formula because I'm telling you the speed of the sound. But the question is, how long does it take sound traveling at 335 meters per second to travel 2 kilometers? Well, that's a speed equals distance over time problem. So we're going to take the speed of the sound, which is 335, you're actually told it, equals the distance, which is 2,000 meters, divided by the time, and get the time. Now, before we do that, in the previous question, I said you'd probably be given a more complicated question. It's the same with this one. I would probably give you this question, but say, how long does it take sound to travel 2 kilometers when it's minus 30 degrees Celsius outside? And by the way, at minus 30, the speed of sound is very slow. Okay. So we take 2,000 divided by 335 and get so close to 6, don't we? 5.97. Let's call it 6.0 seconds. This is the principle of an echo, by the way. That if, and it works very well on a cold day because the speed of sound on a cold day is slower than on a hot day. And all you need is a wall, a building with a fairly decent wall, and you stand half a block away. How many of you have noticed in the winter the sound seems to carry better? Like you get these noises that you wouldn't normally hear. It's because of echoing. And if you stand, say, a block away from that wall or even half a block away from that wall, and you clap your hands once, there will be a clap that returns. And what an echo is that sound wave traveling at that speed, hitting the wall and reflecting back to your ears. You could easily determine the speed of sound using that as an experiment. All you'd have to do would be to measure that time, or that time. I think you'd want a friend helping you out, right? So they're gonna start the stopwatch when you clap your hands, and they're gonna stop the stopwatch when they hear the echo. And that's a time, and then you just have to measure the physical distance between you and the wall and double it and divide by that total time, and you'll get the speed of sound. The way we're going to find the speed of sound will not be using a big distance. We're going to be using distances that are about this big. Number 3, a tuning fork has a frequency of 256 hertz. What is the distance between successive compressions of the sound wave in air produced by this tuning fork at 25 degrees Celsius? I only highlighted fork because I think I have a bracket there in your note package that I need to correct. So that's for my purposes. Well, if you're asked for the distance between successive compressions, what you were asked to determine is the wavelength. That's what wavelength is how far it is from one compression to the next. So going back to this, the distance between that region of high density to the left of the diagram and the region of high density to the right, those are both compressions. That distance is the wavelength. So if you want to find the wavelength, we can use the universal wave equation, which is V equals F lambda, because we know the frequency. The frequency is 256 hertz. The only issue is we need to do a calculation to determine the speed of the sound. But, and I've designed it this way, I don't want to spend a lot of time doing trivial calculations. Number 1, we found that speed. When you look back at number 1, it was what is the speed of sound in 25 degrees Celsius air? And we got 346. Thank you. Bless you. We got 346 So this number, 346 meters per second, is coming from example 1. The frequency is 256 hertz. And we'll talk about what that means in terms of the physical tuning fork in a second. So all we have to do is divide those two, and we'll get the wavelength. So about 1.35 meters. Any questions with any of those? All right. So we're going to be talking about a number of different things over the next little while in this lesson. And we're going to be talking about resonance in air, but in order to understand resonance in air, we need to understand what a tuning fork does. So when I have a tuning fork of 128 hertz, and that's bang on, isn't it? When you take a look at what it's measuring. So this is a very precision-made tuning fork. I have a tuning fork here, by the way. I don't know. Can you read that?
480B. I don't know.
48, just 480?
480.
There might be a letter which signifies a tone or something, but 480, this is 480 hertz. Close, 482. But it's like anything else, right? You can buy an expensive automobile that everything is just perfect, and an automobile where you go to change the station on the radio and the knobs start falling off and stuff like that over time. So when I say a tuning fork has a resonant frequency of 128 hertz, we're learning right now in this question what that means. It means no matter, well, I shouldn't say no matter how much I hit it. I think the tines were hitting each other. That should still be good. It doesn't matter. And if you're watching this on video, we've got a camera set up on a phone app that's measuring the frequency. It doesn't matter whether these are vibrating a little bit. See, it's got some, there we go. It's picking up something else on the app. I don't know if it's a vibration from what, but it's 128. If I hit it harder, it's 128. Well, it was 129. It settles down to 128. What this means, it's like a pendulum. When you get a pendulum swinging, the length of the pendulum determines the period and determines the frequency. It's like the mass on the spring. That, I don't know if anybody really thought of this when you did your lab, but when you put your mass on the spring and measured the period, at no point in time did I tell you pull it down 3 centimeters and let it go. Because the period would be the same. It's the same thing here. A resonant frequency is a frequency that it is allowed to vibrate at. This tuning fork is only allowed to vibrate at 128 hertz. Okay? So just to begin with, you can think of resonant as meaning natural. It's what the structure of the tuning fork is such that it can only vibrate at that frequency. It's like the frequency of a 2-meter long pendulum, or the frequency of a 5-gram mass on a particular spring. Why does it produce a sound wave with the same frequency? Well, I'll explain it and then we can decide to what to write down. When I take that tuning fork and I strike it, this is better, and I strike it, those two tines, and you can see them vibrating back and forth, right? It's a blur. It's a blur because they're going back and forth 128 times per second. But what is surrounding them is air. So what it's doing is it's hammering the air back and forth in the immediate vicinity 128 times per second. And that air is going to vibrate back and forth at 128 times per second, knocking into the air in the next region. That repetition, that continual accordion-like action is what's happening here. Except if you follow this source, this is only going back and forth about, I'll be generous and say 1 time per second. And what happens then, of course, is those air molecules hit your eardrum, and your eardrum vibrates back and forth 128 times per second. I don't know what the air is hitting in my iPhone microphone. It's probably not a physical vibration. It's picking up an electrical signal, and the electrons are going back and forth 128 times per second, and it's doing the magic of computers to tell us it's 128. But if I were to take a different tuning fork, now that's 4,103 hertz. It's supposed to be 4096, so it's off by about 6 hertz or so. You can hear that, right? Now this has a resonant frequency that's different than the 128. But the fact that you can hear it means that it still is capable of knocking the air molecules back and forth 4,096 times per second. And your eardrum is still moving back and forth 4,096 times per second, which tells you that air molecules don't have a resonant frequency. Air molecules are capable of vibrating at a whole range of frequencies. There's not one natural frequency. Your eardrum has a whole range. If your eardrum had a resonant frequency of 128 hertz, the only way we could communicate is if we always used 128 hertz for a frequency. That would be the only sound you could hear. So to put this into words, the tines, when you look at a fork, you have a fork with those 4 pokey things, those are called tines. A tuning fork has 2 tines, vibrate at 128 hertz, causing the air to vibrate at 128 hertz. And I think that's good enough. If the air vibrates at 128 hertz, then you have a sound wave with a frequency of 128 hertz, because that's what a sound wave is, vibration of air. So the answer to the age-old question, if a tree falls in the forest and there's nobody there to hear it, does it make a sound? Yes, because the air will be vibrating. There is sound there. You don't need to have somebody listen to it to have sound there. That's like saying if I remotely turn on a light in the room and you're not there to see it, is there light in the room? Of course there's light. Don't let anybody tell you any different, okay? This leads now to the basic idea of what resonance is. And resonance can be acoustic or mechanical. And I tried to set up a little demonstration to show you mechanical resonance, and I need to tweak it, and I want to show it to you tomorrow. It has to do with pendula. And that if you have a number of pendula hanging, and I get one swinging back and forth, the vibration based on what it's attached to is going to cause energy to be transmitted to the other pendula, but you will discover that only the pendula with the same length as the one I disturbed will be in sync. The other ones might kind of bounce around sporadically, but they will not be in sync. That first pendulum might be swinging like this, and after a while the second pendulum is swinging like this, same period, maybe not as far, but that's mechanical resonance. And I have a video clip I'm going to show you in a second. I'm not a fan of using videos to teach, but it's a 4-minute clip that's a really good teaching tool to talk about mechanical resonance. I mentioned this before with an old car I had that at about, I think it was about 105 kilometers per hour, the whole car just shook like crazy. Like the dash literally was bouncing up and down 4 or 5 centimeters. It would just, and the steering wheel would be doing this. But if you went slower, it settled down. If you went faster, it settled down. And the idea was there was some structural defect with the car that gave it a natural frequency that corresponded to the frequency of rotation of the tires at 105 kilometers per hour. I don't know if any of you have seen this, but you're going to be watching for it now. How many of you have ever seen when you're driving and it's cold out and maybe there's a bit of freezing rain or you have ice on an antenna, that the antenna has this weird vibration to it? You remember when we had the spring yesterday and I was creating what I called that standing wave, where you had those nodes and things were just flipping back and forth. Sometimes you will see that with the antenna, that the top of the antenna is perfectly still, the bottom is perfectly still, but the antenna vibrates back and forth like this, and that has to do with resonance. And I know you shouldn't use your phone while you're driving, but the next time that happens, I feel as though I have to get my phone out and record it, because it's an amazing thing to see. It usually happens, and now you need a car with a metal antenna, that's the issue now. It usually happens if there's a bit of ice on the antenna. I mentioned as well that when the train would go through Stettler, it would cause this, the uprights in the football field would act like a big tuning fork, is what was happening. I was hearing this woo, this very low frequency. So what resonance is the process where I get something oscillating with a particular frequency, and as a result of that, something nearby picks up the energy, but the energy is picked up either through vibrations with the ground or vibrations with something else, or a sound wave. Okay? And if the other object is allowed to oscillate with the same frequency as the first object, there's resonance. You create vibrations in the second place. So it's sometimes called mechanical resonance. Why will a tuning fork struck cause an identical tuning fork to resonate? Well, let me show this to you first. I have this tuning fork, and it's attached to a wooden box for a couple of reasons. The box is open at one end. It amplifies the sound for students. So if you can probably hear it better when I'm facing you. How many hertz is that, Kazia? 259. And when I touch this, I stop the vibration. Whatever air was already in vibration is going to hit your ears, and it's going to be damped out, and we're done. So now I'm going to take this other one. Frequency, same frequency. What I'm saying is, and there's no sound coming out of either of these right now. I mean, my hearing is shot, right? I can't hear much. Nothing in this ear, and the other ear is a little better, but I mean, can you hear that? No more. Is there sound coming out of here? There is. There's not a lot, and it'll hang on for a while. I mean, it's certainly, I like to do this across the room. I'll do it really close, and I'll even point these at each other. So the idea is the air is going to be rushing in at the speed of sound into this opening, causing everything here to vibrate with that frequency, and the tuning fork has a resonant frequency of 259. You can still hear it, eh? I mean, it's not dramatic. I'm going to show you an example of mechanical resonance in a second. But what I want to do first, I'm going to put these right beside each other. You hear it? You can probably even hear it from over there. I've got two magnets. That I'm going to put on here, and that changes the mass of that thing that's vibrating. And in reality, you know what? This is kind of like a spring. The period of vibration has to do with the elastic natures of the tuning fork, K, kind of, and it has to do with the mass. So by me changing the masses, this frequency, I hypothesize, will no longer be 259 hertz. We can check this one again. Steady Eddie, 259. 250. It's a different frequency. So when I put these two together and I hit the one that has a natural resonant frequency of 259, it's causing everything around to vibrate at 259 if it can vibrate at 259, and this can't. You have to take our word for it. There's nothing there. So the reason is they share a natural frequency. Well, you know, I might as well just say they share the same resonant frequency. If one is capable of oscillating at 259 hertz, and I can get the air in the vicinity of it oscillating at 259 hertz without touching the tuning fork physically, then the tuning fork's going to be colliding with those, or those air molecules will be colliding with the tuning fork. Beats. So we have one more thing I want to talk about here. And beats is a musical reference, but it's not what you think. It's not like if you have a 4/4 drumming beat or something that there's a particular pattern. I'm talking about beats which are changes in what we hear based on multiple frequencies. So when you have two different frequencies of sound occurring, then this is something we'll talk about later, but sound has the ability, as do all waves, to pass through itself. This is what makes sound and wave energy transmission in particular decidedly different from particle transmission of energy. Particles can't go through each other. That's why we have collision insurance on our vehicles, right? But waves can go through each other, and we will study that process. That happens to be called interference. So when two sound waves pass through each other, and this is an oversimplification of what's going on, if they have different frequencies, what's going to happen is, as they pass through each other or overlap, there will be places, because they're moving at the same speed but vibrating differently, there will be places where the compression of one wave happens momentarily to be on the compression of the other wave. And when that happens, the two compressions increase the wave energy, and we call that constructive interference. If it turns out that they overlap in such a way where instead of, so I talked about the bottom line already, instead what happens is you get a compression of one wave meeting the rarefaction of another, which means you have the energy pushing the molecules one way, in one wave, and the opposite wave or the other wave trying to do the opposite, pull them apart. You get a canceling of the sound. So what happens when you have two frequencies that overlap that are different is the sound volume goes up and down. Okay? But you can't hear that increase and decrease under normal situations. So if I have, for example, a 256 and a 128 hertz, and that's the 128, it's nice and steady, right? And this is the 256, nice and steady. If I strike them both, it's just louder, isn't it? You don't notice any increase or decrease, and I'll tell you why. The increases and decreases are happening too frequently. I'm going to go back to these, and let's take a look at this one. This should be 256 hertz, right? Or no, was it 259? Yeah. 259. We'll just double check. Yeah, like I said, steady Eddie, right on. Now I've upset the balance here. I hope you understand that if these magnets are closer to the top, I'm probably really going to mess with the frequency. Like the top is where all that vibrational action is happening. Okay. About 10 hertz less. But if I go and put the magnets closer to the base, where the two tines are connected, about 3 hertz less. I'm going to try to get it to be about 257 hertz. 258 is maybe just a little bit too big. I want 257 to make my point. So that's 257. So I'm going to strike both of these at the same time, and it shouldn't really matter where in the room you are. I'll just move this closer to the front of the room. Well, I'll strike them both, not at the same time, but one after the other so they're both ringing. And what I'm hearing there, I'm going to move this up a bit. I'm going to try to hit 258. So this is 259. This is 258. Actually, this might be closer to 257 or 256. What I'm hearing is 1, 2, 3, 1, 2, 3. I'm hearing about 3 beats per second. I'm hearing about 3 beats per second. So I'm hearing about 3 beats per second. This is 250, it's trying to hit 256. Do you see that? Just pretend with me and call it 256. Because after all, I was estimating. And this, of course, is 259. The difference between those frequencies tells us how many times per second those compressions pass through each other. So if one of these is 256 hertz and one is 259, I'm going to hear 3 hertz of frequency beats. 3 beats per second. If I really upset this, and we can make a prediction here, and let's try to count how many beats per second. I know that's difficult. You could measure a 10-second interval and divide by 10, but there's a couple other things I want to show you, and I don't want to rush. I don't know. 9 times per second? It's hard to judge, isn't it? It's a lot more than once per second or 2 or 3 or 4 times per second. I'm going to go with 9. What kind of frequency do we have here? Well, the 259, I don't even know why I checked that one again. And, well, that's not right. It was at 250, it had to settle down. 250. What did I say?
9.
I said 9. Ladies and gentlemen, thank you very much. That was a total fluke. So that's what beat frequencies are. Now I want us to answer a question here about beat frequencies, and then we're done, but I want to show you maybe one of the most amazing things I've ever set my eyes on. And it has to do with what we're talking about, although it's my attempt to show you visually what beats are. Okay? So how often this canceling and adding occurs depends on the individual frequencies. And it's the difference between the 2 frequencies. So if I have a frequency of one wave, which is 4 hertz, and another which is 5 hertz, what are the beats that occur? Now I'm using very simple numbers which are not sound frequencies. They're too low to be sound frequencies. But these could be water waves, or they could be electrical signals of some kind. And what I'm asking is, how many times per second does it go up and down? Do you hear that increase and decrease? And the answer is 1 hertz. It's the difference between them. That's all. That's it. That's what you need to remember about beat frequency. What about if it was 4 hertz and 6 hertz? Well, then you would hear a beat frequency, if you could hear that, of 2 hertz. And I feel as though for next time I teach this, I would change these to frequencies that we can talk about being sound. Okay? This is most likely the question I would ask you on an exam. 2 tuning forks are struck and a beat frequency of 3 hertz is heard. If the frequency of the tuning fork is 250 hertz, what's the frequency of the other tuning fork? What could the frequency of the other tuning fork be? Well, there's a beat frequency of 3 hertz, which means they have a difference of 3. So if the one tuning fork is 250, the other could be 253 or 247. And I don't really know that we need to write anything down for that. We're saying the difference between the two frequencies, and I'm using absolute value because, bless you, because it doesn't matter which one's bigger, has to be 3 hertz. So what are our options? We could have 253 hertz or 247 hertz. For those of you in Math 20, you could solve this equation. By breaking it into 2 equations, one where 250 minus x is greater than or equal to 0, and that will, I believe, end up giving you 247, and then one where 250 minus x is less than 0, and that will give you 253. For those of you not in Math 30 or Math 20, don't worry about it, okay? That's the answer to the question. So any questions with anything we've studied today? A lot of interesting things, but any questions that are on your mind? All right. I have over here a old school cathode ray tube monitor. This thing is heavy. It's probably about 40 or 50 pounds. And they used to make TVs like this, right? You have one like that? Yeah. And they're hard on the eyes, as you can see. Now, I'll move it around so everybody can see things in a bit. But how these work, and I had a cathode ray TV that was huge in this basement of this place I was renting. And when I moved out, I just left it there because it's like hundreds and hundreds and hundreds of pounds. How these work is it's hard to imagine. We study this in detail in Physics 30. If this is the screen that you're looking at here, there's an electron gun that fires electrons, and every time an electron hits the screen, it lights up. A little flash of light. And what happens is that electron gun paints a line from this top left corner to the top right corner and then turns off, goes back, and goes down one line and paints the next line. And it does that. And there might be, I don't know, 1,000 lines here. Probably not on this monitor. There might be 1,000 lines. But it goes from here, top left, to bottom right. Right now, it's doing it. Can't read that. It's doing that with a frequency of 70 hertz, which means it's painting left to right, top to bottom, 70 times per second. Now, when I strike a tuning fork, the tines are vibrating back and forth, and these tines are vibrating back and forth at
288.
288. And 288, if I divide 288 by, I said 75, it doesn't work out perfectly. It's close, but it's off. I'm not saying it's really close, but it's somewhat close. In fact, if I take 288, you said, right? Thank you. If I take 288 and I divide by 75, they're out of sync. But here's the deal. Not only is that flashing at a different frequency that's out of sync than this, but it's flashing from the top down. Which means if I strike this tuning fork and put it in front of there, it's going to be lighting up the top of the tuning fork line at a time. It's going to be highlighting the top and then the next part and the next part and the next part and the next part. Now, if these frequencies were identical, or if this were, when you divided, you got exactly 5, what you would see is the tuning fork kind of standing still. Be like looking at something with a strobe light. What you see, though, is the following. Now, it gets better. That's nothing. That is nothing. I got to stop doing that. Okay? You get kind of a waviness going. I'll use the other knee. Right? But what's happening is it's kind of like we're getting beat frequencies. If you take 75 times 4, you get 300. And this is 288, so they're off by 12 hertz. So it's like things are happening 12 times per second, but again, you're seeing the top of the tuning fork and then going down. I am going to now change the frequency from 75 to 60. And you could do this with these monitors. You could change the frequency because some people's eyes were more sensitive to a flashing. You'd get headaches and dizzy spells after working on a computer for a length of time. So I'm at 60 hertz now. Let's do the one here that was 288 again and see how it looks different. No. Let's take one that is 480.
Yes.
What's 480 divided by 60? 8. It's exactly 8. But I'd be willing to bet, well, you'll have to trust me. Oh, that says, that's going 480. I'd be willing to bet that this is not exactly 480, but they're close. They're really close, right? But they're out of sync a little bit. A little bit. Like this, if I'm bored on a Saturday night, I set this up. I like that look on your face. She's just... Oh, careful. Let's try a different one. Let's try a frequency of 256. What's 256 divided by 60? So it's off quite a bit, right? Oh, sorry. I apologize. Yeah? But let me change it to 85 hertz. What's 256 divided by 85? The closer it is to a whole number,
301.
very close but off a little bit. So it would be the equivalent, when we were listening to the tuning forks and you were hearing wah, 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 that's because the frequencies were very far apart. And that's what we were just looking at with the tuning fork kind of looking wild. Oh, I didn't save it. I want to go to 85. Am I on 85? Oh yeah, it's that kind of screen. Yes, I'm at 85. Oh. Did I go to 85? I don't think I did. I don't think I did. I think I forgot. Oh no, I'm on 60 still. Yeah, I knew the reaction wasn't what I was after. Like I said, one of the most amazing things I've ever seen. I had staff members coming in here, oh, you're doing the tuning fork thing again? And they will sit here for an hour watching this. Now that is 256. I have one more, and I don't know which one is more dramatic. This one is 341.3. I don't know why. It's saying 340 here. But 341.3. Let's call it 340. It's probably between 340 and 341. This is 85. What's 341 divided by 85? 4.01. 4.01. So again, it's very close, but it's off a bit. So the frequencies are very close. This is a visual representation of the beat frequencies. If the frequencies are close, you should see beats with a very low frequency, which means it looks very wavy. I think that might be the best one. I like this one best. You like the other one better? Ah, okay. So I'll show you guys the other one here. Yeah. Oh, yeah. Okay. So it's kind of a. Show us the other one. Okay. Like, that's wild. You, of course, know that it is not actually doing that, right? It's just lighting up the top section when the tuning fork tines are here, and then when it lights up the next section, they're a little bit closer, and then they're a little bit closer. So it's like a, you guys have seen a strobe light before, right? If you flash a strobe light on a spinning object, maybe you haven't. Maybe I'll show you that tomorrow or the next day. You can get things to slow down. We use it in Physics 30 because we know that if you pass electricity through something, we can cause it to vibrate 60 times per second. But it's just a blur. But when you hit it with a strobe light at 60 hertz, it's frozen. Because you're lighting it up every time in the same place. And if you change the frequency a little bit, then the thing starts to kind of do this thing. Anyway, this isn't beats that you're looking at. It's just my way to show you beats. And I hope I never lose this baby because it's really important to me. So that's it. You have some questions connected to all of this, dealing with the speed of sound, dealing with beat